Good morning, students. Estimation part 5 is the last video of the theory of estimation. So, fourth criteria of good estimator is sufficiency. Sufficiency is very, very important. So, we have to identify the sufficient estimator to estimate the unknown population parameter theta. So, this is the definition. An estimator is said to be sufficient for a parameter theta, if it contains all the information in the sample regarding the parameter. So this is a simple definition of sufficient estimator. Sufficiency. If Tn is a function of sample observation, is an estimator of parameter theta, unknown population parameter theta, based on a sample of size n from the population with the density function f of x comma theta, such that the conditional distribution of x1, x2, and so on, xn given t is independent of parameter theta. So t is called sufficient estimator of population parameter theta. So this is a very, very important definition. So for example, I am giving one example using this definition and identify the sufficient estimator. So let here xi follows Bernoulli distribution 1 comma theta. Now E of xi is equal to theta, variance of xi is equal to IIDs theta into 1 minus theta. Let T is equal to summation xi, I is equal to 1 to n, is follows binomial n comma theta. The probability of T is equal to small t, that is equal to NCT theta power t 1 minus theta whole power n minus t. T is equal to 0, 1, 2, and so on up to n. Now the definition, apply the definition. So x1, x2, the conditional distribution of sample observations given t is equal to the probability of x1, comma, x2, comma, and so on, xn, x1, x2, xn are IIDs, intersection t by probability of A given B formula, probability of A intersection B by probability of B. So now here is all are independent. So now here is x1 into probability of x2 into probability of xn. Here is the intersection probability of t is equal to small t dividing by probability of t. Now here is theta power t, theta power x1, 1 minus theta whole power 1 minus x1, theta power x2, 1 minus theta whole power 1 minus x2, and so on, theta power xn, 1 minus theta whole power 1 minus xn, intersection NCT theta power t 1 minus t whole power n minus t. So dividing by NCT theta power t 1 minus theta whole power n minus t. So now the common part of the numerator is theta power summation xi 1 minus theta n minus summation xi, intersection theta power t 1 minus theta whole power n minus t dividing by NCT theta power T 1 minus theta whole power n minus T. The common part of numerator is theta power T 1 minus theta whole power n minus T. Here summation xi is called T. This is summation xi is called T. The common part of these two theta power T 1 minus theta whole power n minus T. Dividing by NCT theta power T 1 minus theta whole power n minus T. These two cancel. The remaining part is 1 by NCT. This is independent of parameter theta. So we can say that T is a sufficient estimator of parameter theta. T means what here? Summation xi is sufficient estimator of theta. This is the procedure using the definition. So using this technique or definition, easily we can identify the sufficient estimators. So, but it's very typical one. It take more time. So, in this situation, the Niemann developed the factorization theorem. The Niemann mathematician identified the factorization theorem. So the Niemann was given by the factorization theorem. Factorization theorem is a very simple theorem. Using this factorization theorem, easily we can identify the sufficient estimators. Let T is equal to T of x is sufficient for theta if and only if the joint density function, that is called likelihood function, say the joint PD of the joint probability mass function is denoted as L, that is say of the sample values can be expressed in the form L is equal to G of T of x into H of x. The likelihood function already explained. The likelihood function can be expressed as G of T of x into H of x, where T of x is the G of T of x depends upon theta and x only through the values of. Here is the function of x values T of x and H of x is purely function of x independent of theta. T of x and H of x are function of sample observations independent of theta, but G of T of x depends on theta. So the likelihood function can be expressed in this form. So the T of x is said to be sufficient estimator of G of theta. T of x is said to be sufficient estimator for T of x is sufficient estimator of parameter theta. The original sample x is always sufficient statistics here. Remember here. Sometimes we cannot identify the suitable sufficient estimator. In the situation, the original sample x, drawn sample x1, x2, xn is always sufficient estimator parameter theta. One more criteria, Fisher-Neyman criteria. After factorization theorem, the Fisher-Neyman identified the one more criteria with the help of the PDFs. A statistics T1, function of sample observation, is sufficient estimator of parameter theta if and only if the likelihood function can be expressed as L is equal to pi, I is equal to 1 to n f of xi comma theta, g of t1 comma theta into k of x1, x2, xn. The k of x1, x2, xn is purely function of sample observations independent of parameter theta. G of t1 comma theta is a depends on theta. This t1 is the PDF. Here is PDF of t1 is a statistic. So now here is g of t1 comma theta is a PDF of t1. PDF of t1 depends on theta. The probability differential function of statistics t1. K of x1, x2, xn is a function of sample observations only, depends on. So K of x1, x2, xn is a function of sample observations only independent of theta, not dependent, independent of theta. Using this factorization theorem or Fisher-Neyman criteria, we can identify the sufficient estimators. Remark, very, very important remark. The most general form of the distributions admitting sufficient statistics, Koopman's form. Koopman's form is a very powerful form. The likelihood function can be expressed in the form of L is equal to g of x into h of theta into e power a of theta into psi of x. The likelihood function can be expressed like this here. H of theta and a of theta is depends on theta. So g of x and psi of x are functions of sample observations. So independent of theta. The above equation represents the famous exponential family distributions. Famous exponential family distributions, of which the common distributions like binomial exponential distribution, family of exponential, Poisson family of exponential, and normal also family of exponentials with unknown mean and variances and are members. Binomial, Poisson, normal are members of the exponential family distributions. So now the above equation represents of the famous family of exponential distributions. So sometimes here we have to use these Koopman's forms and identify the sufficient estimators. Now examples, suitable examples. Solid examples. Example 1. X follows Bernoulli 1 comma theta xi. Xi's are IIDs 1, 2, 3 and so on. Sufficient estimator. Sufficient estimator of theta is dash. Solution. The probability mass function of x is P of capital X equal to small x, theta power x, 1 minus theta whole power 1 minus x. The likelihood function phi I is equal to 1 to n P of xi comma theta. Phi I is equal to 1 to n theta power xi 1 minus theta whole power 1 minus xi. L is equal to apply this expansion this one. After expansion we get theta power xi summation xi 1 minus theta whole power n minus summation xi. Now this likelihood function can be expressed as likelihood function by factorization theorem. L can be expressed as g of t of x into h of x. G of t of x theta into h of x. T of x, h of x is a function of sample observation. Now L is equal to theta power summation xi 1 minus theta whole power n minus summation xi into 1. Now this is g of t of x under theta into h of x, where g of t of x is equal to theta power summation xi 1 minus theta whole power n minus summation xi. H of x is equal to 1. Here 1 means here function of sample observations. This 1 can be written as x1 power 0, x2 power 0, and so on xn power 0. Any power 0, 1. Function of sample observations. Therefore, Tx, where Tx is equal to summation xi, is sufficient estimator of parameter theta. Sufficient estimator of parameter theta. By already explained, by using definition, so we get summation xi is sufficient estimator for theta of Bernoulli population. By using factorization theorem also, so summation xi is sufficient estimator parameter theta. One more example, example 2. Let xi follows Poisson lambda, I is equal to 1, 2, and so on, n. Sufficient estimator of lambda dash. The probability mass function of Poisson distribution x, p of capital X equal to small x, e power minus lambda, lambda power x by x factorial, x equal to 0, 1, 2, and so on. The likelihood function is equal to pi. Pi is equal to 1 to n, p of xi comma lambda. Now, pi I is equal to 1 to n, e power minus lambda, lambda power xi by xi factorial. L is equal to e power minus n lambda, lambda power summation xi by pi xi factorial. Now this likelihood function can be expressed as g of t of x under lambda into h of x, where g of t of x under lambda is equal to e power minus n lambda, lambda power summation xi. H of x is equal to 1 by pi xi factorial. P of x is equal to summation xi. Therefore, P of x summation xi, I is running from 1 to n, is sufficient estimator for lambda. Sufficient estimator for lambda. So this is the procedure. By factorization theorem, easily we can identify the sufficient estimators of the unknown population parameters. Next, another example. Let xi follows exponential parameter theta. Xi's are IIDs. I is equal to 1 to and so on n. Sufficient estimator of theta dash. PDF of x is f of x is equal to theta into e power minus theta x. X greater than 0. Likelihood function phi I is equal to 1 to n f of xi comma theta. Phi I is equal to 1 to n theta into e power minus theta xi. L is equal to theta power n e power minus theta summation xi. So this can be expressed as g of t of x under theta into h of x. Now L is equal to theta power n e power minus theta summation xi into 1. Now g of where g of t of x under theta is equal to theta power n e power minus theta summation xi. Summation xi into here is this is g of t of x. H of x is equal to, that is 1 function of sample observation constant. T of x is equal to what? T of x is equal to, in this one here, the function of sample observation is what? Summation xi is a function. I is equal to 1 to n. Therefore, T of x summation xi I is equal to 1 to n is sufficient estimator of parameter theta. Exponential distribution summation xi is sufficient estimator of population parameter theta. Example 4. Let x follows normal distribution mu comma sigma square xi's are IIDs. I is equal to 1, 2, 3 and so on up to n. Sufficient estimator of mu and sigma square dash. Jointly sufficient estimators mu comma sigma square. Solution. PDF of x is f of x equal to 1 by sigma root 2 pi e power minus half x minus mu by sigma whole square. Now, here the likelihood function of normal distribution phi I is equal to 1 to n of xi comma theta. Theta belongs to mu comma sigma square 1 by sigma root 2 pi whole power n e power minus 1 by 2 summation I is equal to 1 to n xi minus mu by sigma whole square. L is equal to 1 by sigma root 2 pi whole power n e power minus half summation 1 by 2 sigma square. Sigma square is known cases here. Unknown case is taken outside. Summation xi square plus mu square minus 2xi mu. Apply a minus b whole square formula. Its likelihood function 1 by sigma root 2 pi whole power n e power minus 1 by 2 sigma square summation. Apply summation here. Summation xi square n mu square. Apply summation. Mu square is a constant value. N times here n mu square. 2 mu summation xi. Summation xi. Now L is equal to sigma root 2 pi whole power n e power minus 1 by 2 sigma square. This is T1 plus this T2 n mu square minus 2 mu T1. T1, T2 are statistics where T1 is equal to summation xi, T2 is equal to summation xi square. L is equal to g of t of x, g of t of x into h of x, where t of x is equal to T1 comma T2. H of x is equal to 1. Likelihood function L is can be expressed as g of t of x under parameter theta into h of x by factorization theorem. T1 summation xi I running from 1 to n is sufficient estimator of mu. Sufficient estimator of mu. Sufficient estimator of mu. P2 is equal to summation I is equal to 1 to n xi square is sufficient estimator of sigma square. Therefore, summation xi square jointly sufficient estimators of mu and sigma square. Here is very, very important remark. For examination point of view, remark is very, very important. X follows normal distribution mu comma sigma square xi. Xi's are IIDs. Here is remark 1. Special cases. Sufficient estimator of mu is equal to x bar when sigma square is known case. Sigma square is known. Second one, sufficient estimator of sigma square is equal to 1 by n summation I is equal to 1 to n xi minus mu whole square. There is sufficient estimator for sigma square. 1 by n summation I is equal to 1 to n xi minus mu whole square. When mu is known. Third one, sufficient estimators of mu and sigma square is equal to jointly sufficient estimators. Here is x bar and capital S square, where capital S square is equal to 1 by n minus 1 summation xi minus 1 xi minus x bar whole square. Note, important note. X bar is not sufficient estimator for mu when sigma square is unknown. Capital S square is not sufficient estimator for sigma square when mu is unknown. Remember this remarks and important note is very, very important for examination point of view. Don't confuse here. A jointly sufficient estimator of mu and sigma square x bar s square, which is equivalent to summation xi square. Already so defined here. Summation xi square is equivalent to x bar and capital S square. So different techniques are there. By technique here we have to identify the sufficient estimators for sample mean and population mean and population variance. One more example. Let xi follows uniform distribution a comma b. I is equal to 1 to and so on n. Sufficient estimators of a and b dash. F of x is equal to PDF 1 by b minus a less than or equal to x less than or equal to b. Here the range of x depends on parameters. In this case, use order statistic method. Already this method is applied to identify the MLEs. Similarly, how to use this one. So A less than or equal to x1 less than or equal to x2 less than or equal to. This is the shortcut technique. No need to take factorization theorem or Fisher-Neyman criteria. Actually, for descriptive problems, either factorization or Fisher-Neyman criteria solve this problem. But entrance point of view, directly apply the order statistics technique. A less than or equal to x1 order less than or equal to x2 order less than or equal to less than or equal to xn order less than or equal to b. Now here in this case, the minimum value of A is the maximum value of A is x1 order. The minimum value of B is xn order. Therefore, by using the Saxena technique, here is we consider the maximum value of left side parameter is x1 order. The minimum value of right side parameter is xn order. These two are the sufficient estimators for jointly sufficient estimators for A and B. Therefore, sufficient estimator of A is equal to x1 order. X1 order means the minimum xi, minimum of xi. Shortcut technique. Sufficient estimator of B, xn order, maximum xi. Therefore, x1 order, xn order, jointly sufficient estimators for A and B. This is the very important technique. Next problem 6. Let xi I is equal to 1 to n be a random sample from the distribution of x comma theta is equal to e power minus x minus theta x greater than theta. Theta lie between minus infinity to plus infinity. Solution f of x comma theta is equal to e power minus of x minus theta x greater than theta. Range of x depends on parameter theta. Use order statistic method to find sufficient estimator for theta. So here is theta less than x1 order, less than x2 order, less than and so on, less than xn order, less than infinity. The minimum value, the maximum value of theta is x1 order. The maximum value of theta is x1 order. Therefore, sufficient estimator for theta is x1 order. Here, theta is left side of x. Theta is left side of x. So one more example. For understanding purpose, we have to solve as many as problems. Let xi's or iids follows uniform 0, theta. I is equal to 1 to and so on n. Sufficient estimator of parameter theta is dash. Solution. F of x equal to 1 by theta, 0 less than or equal to x less than or equal to theta. Range of x depends on parameter theta. Theta is right side of x. Now consider the order statistics. In this case, use order statistics technique. 0 less than or equal to x1 order less than or equal to x2 order less than or equal to less than or equal to xn order less than or equal to theta. The minimum value of theta is xn order. Therefore, xn order is sufficient estimator for theta. So, several examples are explained.